Hi, we are now ready with the tools to study control. So we have so far studied linear control systems, specifically linear second order systems we have seen. We have seen how to study its behavior using the roots of its characteristics equation. We have seen how to analyze such systems using transfer functions and state space representations also. So at least we are now ready to study robot control. So let us now study controlling any robotic joint to begin with. Okay, so let us start. So let us just recall the theory of working of a DC motor that we have seen earlier in module 2. So yes, this is the first thing that we have learned. So we saw the structure of a DC motor. Basically it contains a simple armature coil that is shown here, correct? And you see it has a current that gets into that is given by IA, that is the armature current, comes out from here. It develops a torque which is given by tau. Not much parameters which are here to observe. First thing that I want to point out is this equation, that is robot torque, that is the joint torque that the rotor of a motor that is seen is proportional to the current, and obviously there is something called as sine sigma. Sigma is angle between B and A. B is the field direction and A is the normal to this area. That is the direction of normal to the area. If this is the area, so normal is this, so that is the area. So you see, if you have multiple coils which are there, which are at, let's say you have multiple poles and multiple coils, so this becomes almost insignificant, and in that case tau is proportional to current that is flowing through that. So this torque basically it varies in sinusoidal manner. It comes up, it goes down, and if you have multiple coils, so by the time one of them dies off, next one gets in. So you have, let's say, 32 poles or maybe 20 poles or something like that. So if at all you have multiple number of poles, so that evens out the torque which is coming due to this change. Okay, so tau is equal to Km into Ia. So this is the first thing that we have seen, and also higher is the applied EMF, that is the voltage, higher is the speed that we have seen. We'll see now why it is happening also. Okay, so this is first thing that I have pointed out earlier, and higher is the speed, higher would be the back EMF. Now what is the back EMF? Just let us go back to the slide once again. So if you are providing current from here, so you see you should feel forces, that is the couple of forces which are there, that is creating a couple basically. So that is effectively creating the torque which is aligned like this. So yes, if at all you are providing current, it produces torque. If you don't provide any current and the rotor keeps on rotating due to its inertia, let's say while you want to stop your motor, so in that case what happens, as soon as you stop flowing this current, this is the conductor which is moving inside this field. So field is always there. So you see you have field which is always there. So field is there, okay, and you have conductor which are like this. Okay, so conductors are there. So if that is moving, it automatically induces a current in this conductor. Okay, so that is there. So even if you don't provide any current from outside, due to its own motion within the magnetic field causes some current to be induced. So that current is in a reverse direction. So cause and effect. So if this is the cause which is creating this current, so effect will be the current that creates a reverse torque so as to stop the motion. Correct? So it is known as a back EMF. Okay. So higher is the speed, higher would be the back EMF. So this basically limits the maximum speed of any series wound DC motor. Series wound DC motor. In case of series wound DC motor, if back EMF is there, that effectively reduces the incoming current. Okay. So total current which is flowing through the armature greatly reduces. At higher RPM it is very significant, and that causes reduce in torque. Okay, torque getting reduced. So that is basically limiting the maximum speed of this. Okay, so that is the reason why speed is limited. In series wound it is more significant because the same current flows through the armature also. Okay, so that is there. And higher is the current, higher is the torque, that you have already seen. In case of multipole DC motor, it is directly related without any relation with sine sigma that you have seen in case of that. And reversing the polarity would change the direction of rotation, because that would create the forces that is induced in the coils. So these forces, this force direction will be reversed if you reverse the direction of current, and that will create a reverse torque. Okay, so these points should be noted before we begin. So okay, let us begin with the robot joint. So we'll discuss the dynamics of a DC motor. So this one in particular is electrical model that I am going to discuss. So yes, this is the applied voltage across the terminals of your motor. Okay, let us say it has its own internal resistance. Coil resistance is given by Ra, that is armature resistance. Because it is a coil, it is a copper which is wound over a core. So yes, it behaves very much like an inductor also. So this has an inductance of La. Okay, and I know there is a back EMF. So this is a back EMF constant, and that is giving a reverse voltage which is proportional to, you see, back EMF voltage. This gets positive opposite to this. So back EMF is there. So this is back EMF constant and theta m dot. What is theta m? Theta m is the speed of your armature. Okay, speed of your armature. So the higher is the speed, higher is the back EMF. That is what I told. So these are the basic relations, okay, that you already know from your previous slide. Okay, so Ia is the current flowing through the armature. Motor constant is Km. Now back EMF voltage is proportional to speed, angular velocity of the rotor, and back EMF constant is given by Ke. Okay, so now putting them all together, what I can write is this closed circuit has got potentials across each of them. So summing them all together should count to 0. So yes, this is the applied voltage. Okay, applied EMF. Okay, that is the driving voltage, and this is your back EMF. So subtracting them should give you the effective voltage which is present in this loop. Okay, that is what is causing the potentials to be generated across resistance and across the inductance. So across inductance it is La, that is inductance of the armature winding, into dIA by dt, rate of change of current. So voltage induced across inductor is inductance, that is the constant, into rate of change of current. So higher is the rate of change, higher is the voltage that is induced across this inductance. Okay, so this is first. These are basic physics equation that hopefully you have gone through during your higher school also. Okay, and voltage across this resistance is Ra into Ia. This is simply by Ohm's law. So yes, Ia into Ra plus L di by dt should be equal to total potential which is there across this. Okay, so this is the first fundamental relation, that is the electrical relation of this DC motor. Okay, okay. Now let us look into the mechanical model also. We call it the actuator dynamics of the robot joint. So yes, it is constructed like this. So you have tau m that comes here. Okay, that comes here, that is through the motor. Okay, and Ia is basically the moment of inertia of this armature, whole of the system including the coil. All solid armature core is here. Okay, including the shaft. Okay, everything is here. And you have theta m, that is the joint angle at an instant of time. You have bearings that goes here, 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 here. Altogether, let us say you have a bearing constant, that is basically the damping coefficient is given by Bm. Okay, and you have a gear ratio over here. There is a transmission. This is the smaller one, this is the bigger one. Overall, it reduces the speed when it comes to this and enhances the torque. So yes, that torque which is transferred to the link joint is tau L. Okay, so tau M is the motor torque, tau L is the shaft that connects your link. Link has its own moment of inertia given by IL, and the shaft rotates by an angle theta L. You also have damping coefficient over here, that is BL. Okay, so these are the parameters. Overall, whole of the mechanical system can be visualized like this. So now let us start forming the dynamic equation for this. So rotor inertia will be armature plus inertia of the gears. So gears are also attached with armature. So total inertia Im, that is the inertia of the actuator, should be equal to Ig plus Ia. Armature plus gear, total inertia is like this. Okay, axis of rotation remains the same. So it can be simply scalar added. Okay, so equation of motion of the actuator can now be given as, so effective torque that is coming from the link side of it. So if this has a torque which is tau L, which is here, so the torque which is coming, resistance torque which is coming onto the motor shaft is tau L by eta. So yes, this is tau L by eta that is reflected out here. Okay, and tau M is the driving torque. So net driving torque due to both of these is tau M minus, this is the reaction torque which is coming onto this, that is tau L by eta. Tau L by eta. So that comes here. So that is actually driving your shaft. So it is Im theta m double dot, moment of inertia into angular acceleration, plus B theta m dot. Bm is the damping coefficient into angular velocity. So this is the total torque which is here. So yes, this is the torque which is developed due to the inertia. This is torque which is developed due to the damping. Total torque should balance out each other. So that is here. Okay, and also tau M is Km into Ia. You already know the torque which is generated out of your motor is Km into current that is flowing through that, rest remains the same. Okay, so these are the parameters I have already discussed there. So theta M is motor shaft rotation angle, tau M is generated torque applied to the rotor, tau L is the load torque, eta is the gear reduction ratio, Bm is coefficient of viscous friction. So yes, the reason why this is here is very much clear from here, hopefully. So yes, angular velocity is eta time reduced. Okay, so if angular velocity is reduced, torque is increased from the L side of it, because you know tau L theta L dot should be equal to tau M theta M dots. This is angular velocity into torque, angular velocity into torque, that is work done at the input should be equal to work done at the output. So if it is theta L dot is theta M by eta, theta M by eta, theta L dot is theta M by eta, that is there. So effectively tau L becomes equal to eta times of tau M, or tau M side of it will see if the rotor is static, if the rotor is static, but if it is moving, you see tau L by eta times coming to the motor side of it, that is as a reaction torque. Okay, so yes, I am wiping them all so as to make it very clear now, and same happens to the acceleration also. You see theta L double dot is equal to theta M double dot by eta. and tau L is eta times of tau M. So these are some fundamental mechanical relations which should be quite clear. Okay, they are simple work input and work output relation that is shown here. Okay, and this is dynamic equation of motion. Okay, yes. So now moving ahead, let us see what else we can put in here. So load torque also drives something. It drives the link. So it is moment of inertia of the link into angular acceleration of the link. Got it? And you also have damping over there. So it should give you damping coefficient into angular velocity of the link. So total torque is driving all these. Okay. So yes, now equation 2 can be put to your actuator equation, that was equation 1. Okay. So it looked like this, if you remember. So I'll just put tau L to this, okay, or this, and I'll bring it over here. So what should I see now? So it quickly can give me, so if I substitute tau L over there, so it should be put over here, and that is equal to tau M or Km into Ia. So this is the overall relation that is there. So in terms of motor variables theta M and tau M, I'll substitute these two equations once again. So I'll put theta L is equal to theta M dot by eta over here. So theta L, wherever I see, I'll put theta M dot by eta. So that should give me, if I take all of them common and bring them out, similarly theta L double dot should be equal to theta M double dot by eta. So effectively eta square is going to come. So you see this equation. So it is Im IL by eta square into theta M double dot plus Bm plus Bl by eta square theta M dot is equal to tau M. Okay, so this is quite clear, is a straight relation. You can try getting it yourself also. Okay, in terms of load variables, if I convert, so I'll substitute otherwise, that is theta L, I have substituted earlier, theta L dot is equal to theta M dot by eta, and theta L double dot is equal to theta M double dot by eta. So I'll substitute it otherwise this time. I'll substitute theta M dot is equal to eta times of theta L dot. So that going here, okay, and here, okay. So it should be theta L into eta is equal to theta M double dot. So these two values I'll put here and I can get this relation. So this is the load side variables, okay, and this is in terms of motor side variables. Okay, now let us see what does these two equations tell me. So effective inertia is IL eta square Im. So this is the effective inertia which goes to the motor. So that is what actually comes. So output link side of the gearing. So total moment of inertia, what the output link side will feel, is due to its own inertia and due to the rotor shaft inertia. Okay, that is multiplied, you see. So more inertia you will feel. So total inertia is eta square Im plus IL. So output link side due to the gearing you can see, and similarly in the motor side of it, motor will see the link inertia is reduced by eta square times. Okay, if eta is normally ranging, in case of industrial robots, it ranges from 100 to 300 gear ratio is there. So in that case you can imagine it is reduced up to eta square times. So all the rotor plus this inertia, now you will see this is almost like missing from your inertia. So motor shaft inertia will only feel this one. Hardly there is any effect due to the link moment of inertia, okay, due to the gearing. So that is the reason I told you earlier also, that is the reason why we can drive industrial robots using single input single output system. Okay, So yes, now looking at the damping side of it, same will happen to the damping also. So from the load side, you see you have damping which is here. Okay, it has more damping. Okay, it is very much damped. So, okay, naturally damped. Okay, and you also see from the motor side again, you see you have less damping due to the load side of it, and total damping has increased also, but to a very less extent is coming from the link side of it. So motor side will see this much of damping, that is here. Okay, so this is the damping, and normally eta is very greater than 1. So this allows effective inertia as seen from the motor side to be constant. So from the motor side, the inertia which is there is almost constant. It is hardly getting affected by the inertia of the links. Okay, so this is the reason SISO is quite good to be adapted in controlling industrial robots. Okay, IL varies with the load. Link moment of inertia varies with the load due to the supplementary load. Even with the end effector load, if it is carrying, moment of inertia is going to change. Okay, so this should be noted. Okay, so now let us get the transfer function of the joint so that I can get to the input and output relation for this DC motor system, that is whole of the actuator here. So these two are the fundamental equation that we have derived just now. This was the electrical relation and this is your mechanical relation. So I call it electromechanical models. So taking Laplace of this and this will lead to this. Okay, so you can quickly see it here. So IA can be written as IA S times of IA is constant, current is varying, so IA S into S. So S goes here, so S is now taken out with this, and similarly Laplace of IA will be IS. So taking common, I get to this. Right hand side of it, VA becomes VAS, K is constant. So again, because it is theta m dot, it is S theta m S. Okay, taking all the initial conditions as 0. The rotor has started from rest, 0 velocity, from 0 position, right? So that is the reason this is valid, and then taking Laplace of this will give me this. So it is theta double dot, it should give me Im S square, and theta ms will come out from both of these. Okay, similarly from the right hand side you have constants which are there. So theta ls is constant, so tau ls is constant, and you see this. Okay, so these are the two. So can I draw whole of this? Before I do this, let me just start with little fundamentals first. Okay, fundamentals of transfer function. Before I can make you understand this one, I'll discuss a bit on that. Okay, so let us start. So transfer function, you know, it is input, that is IS, and you have a transfer function, as you have seen, it is Laplace of output by input. So it is output Laplace. So output by input transfer function is given as output by input. This is quite okay. Okay, so now again, so I'll extend this idea further. So if it is in series, you have two blocks coming one after the other. Okay, so this becomes your input, this becomes your output. You have transfer function 1 and you have transfer function 2. Okay, so you can write it as, let us say there is some thing, that signal which is tapped over here is this. So T1S is equal to ES by IS. Similarly, T2S becomes equal to OS by ES. So multiplying them together will give me T1 let us forget about S now. T1 into T2 should give me E by I and O by E. So effectively ES will get cancelled, so it gives me output by input. So you see, if they are in series, they can be multiplied. So you can directly get an equivalent block diagram of equivalent transfer function as T, that is T1 into T2, that will directly relate the output to the input. This is the first thing that you should know. So this is your, if they are in series, okay. What will happen if it is in parallel? So if it is in parallel, let me just wipe it off. Okay, so I can draw it like this. So if it is in parallel, you cannot draw the way it is drawn for serial. This is your block, this is another block, and signals from both of them is now added over here, and it gives you a further output. Okay, so this is added from here, this is signal coming from here is added. You have T1 and you have T2. This is your output, this is your input. Okay, so this time you see there is a signal which is from here. So let us say this is O1, this is O2S, O1S and O2S. So T1 will be equal to this, let it be this O2 and this one as O1. So it is O1S by IS, and similarly T2 will be equal to O2S by IS. So if I add them together, what will I get? T1 plus T2 will be equal to O1 plus O2 by IS. So O1 plus O2 is nothing but output by input. Got it? So that becomes the equivalent transfer function in this case. So this is your T1 plus T2 is output by input. So in case of parallel, it gets added like this. Okay. Now let me again wipe it off and show you one more example. Okay, now let me draw it in a closed loop way, because the way we want to do it now is a closed loop application. So this becomes your input that comes here to the summing block over here, that is plus. This goes to a transfer function which has GS, and that is your output. You have a tapping from here that comes through an feedback line which is here, that is HS, and that comes here with a negative sign. So this is your input, okay, and this is your output. Okay, now let me see what should be the equivalent transfer function that connects the output to the input. Okay, so the signal which is seen here now, let us say if it is ES, so ES is nothing but ES is equal to difference of these two. So IS minus OS signal is getting multiplied here, is coming here. So OS into HS. So that comes here. Okay. So that is getting multiplied, and GS may be written as OS by ES. So substituting this ES here, okay, so what I should see now, and rearranging that will give me a direct transfer function that relates the output to input, output by input as, that is the equivalent transfer function of this. So that is equal to, so I'll put it here so that it is clearly visible to you. So the transfer function now can be evaluated as GS by 1 plus GS into HS. So this is known as a feedback transfer function. This is the system transfer function, input and the output. So equivalent transfer function this time is this. You need to remember this. We'll be using this now. Okay, so this is the reason I have discussed this in so much detail. So yes, so this is your GSY 1 plus GSHS. The system structure is very much like this. There are many other transfer function rules. I won't discuss it here. But yes, this is how you can handle them in blocks. So that is the beauty of arranging them in transfer functions. Okay, so yes, now let us come to our problem now. Now I'll move here. So yes, this is your first thing that I want to discuss. Okay, let me come back to my slide also. Okay, so this was there. You saw till here. I want to come to this now. Okay, how these two equations are holding true and they can be clubbed in this manner. Okay, they can be clubbed in this manner. Okay, so that is what I am going to discuss now. So now when this part is there directly, okay, you have input here, you have output here, and let us forget there is any disturbance which is coming from the link side of it. Okay, so if this is not there, so I'll just write one by one what all systems that comes in. So yes, you see, if I leave this out for now, so this and this is in series. So you can draw equivalent transfer function for all of these together as this. So it is product of 1, 2 and 3 terms will come here. 1 into 2 into 3 will come here, and that is going out. You see, you have S theta M S which is written here, and you have KE which is here, and you have a block that is shown here. This is your input VAS, that is the voltage from to the armature. Okay, so that comes here. So this looks like very much like a closed loop system, okay, with feedback as KE, and this is coming here and this is whole. So yes, total transfer function for all of these system that starts from here till here, okay, from here to here, equivalent transfer function can be given by this, and that can be calculated as output, that is S theta M S by input VAS should be equal to GS. So it is product of all these three. So it is 1 into 2 into third term by 1 plus 1 into 2 into 3 into KE. Got it? So I'll just make myself vanish a bit. Okay, so this is what I am talking about. So output by input should be equal to product of the terms 1, 2 and 3 which are shown here, here and here. Okay, divided by 1 plus GSHS. Okay, so that is KE that comes here, and this one that goes here and here. Okay, so output is this, input is this. So this is the first thing that is there. Now again, you see what all equations that I want to put here. Okay, the first equation. So let me just come back to the previous slide. Okay, so this is what was there. Just see if it is correct or not. First let us try and get to this block diagram first. Okay, so the first equation, where is it located in the transfer function system? Okay, so this is VA minus KE S theta MS. So S theta MS signal is coming to this feedback. So this is getting multiplied with this. So over here you see you have KE into S theta MS that comes here. Okay, so this minus this is getting into this line. So here you see you have exactly this one. So I'll just mark them here. So this value is visible here. Okay, so this into this gain, now the value which is here into this gain should be equal to this. So that is what is written here. So if you multiply the value which is here, that is here, into 1 by IAS RA, 1 by IAS RA gives me IAS. So that is IAL. So you have understood how this equation is put to the variables which are lying in this line. Okay. Now let us see the model which is coming next. Okay. Now Km, let me use another ink this time. So Km into IAS, that is getting here. Okay. Minus tau L eta, tau L by eta. So Km IAS minus tau L by eta, okay, is now coming here. So this signal is this one from here to here. Okay. So this into 1 by Is plus Bm. So this is here, and the term which is here is S theta ms. So this into this should give me this. Got it? Stepwise. Okay. So I'll tell you once again. So this into this should give me this. So that is what is put here. Okay. And I have brought in this S which is inside to this. Okay. The S which is here. So I have put that inside to this bracket. Okay. And I should see Is square plus BMS. Okay. So that is what is here. So these two equations are clearly put to this transfer function, and whole of this can now be compacted using the approach that I have discussed here. So I will make a transfer function of all of this. So in the first case, I am excluding the disturbance which is coming from outside, that is this term, taken the product of all these three and created a closed loop over here with this one as the system. Okay, electromechanical system. So this is electrical, this is mechanical part of it. So that is sitting here. This is your output of the closed loop that comes here, and this is your input, that is VAS. This is your feedback. Okay, so equivalent transfer function can now be given as this one. Okay, that is this part. Okay, again look at otherwise. Okay, this time let us say it is driving by itself, that is it is being driven by the load. So in that case you are not applying any external voltage. Okay, so this is totally absent. So in that case load torque will be visible. Okay, with gear reduction ratio it is coming onto the system, mind it. Okay, so this is always there. So this is the driving torque, and whole of the system is now getting driven by that. Okay, so what all things that goes in series is S times of theta ms into Ke. Oh, okay, so this is your output. So in the feedback, what all things are getting in? So this becomes your input. This becomes your output. Okay, so output is S theta ms. So S theta ms by input you have tau L by eta, that comes here. Okay, so that is visible from here, output by input. Feedback is this time positive. So if you apply 1 by 1 plus GS by 1 plus GS HS, so HS is this. Okay, so that is basically over here it goes with a negative sign. So you have to take the product of this coming to this and this. So whole of this are in series now. Okay, whole of this are in series. So minus of Ke will be visible because you see you have a negative sign over here. So Ke into, so you have total terms which are there in the HS side of it, that is the feedback side, will be Ke into 1 by minus Ke into 1 by IAS RA plus RA into Km. So all these will be there as HS block. This is your input, this is your system. Okay, this becomes your GS. So GS is here if you remember. So this is your GS, and that is your output and input. So now you can write the closed loop transfer function. Got it? So there are two approaches to it. First, the robot is getting driven by the input voltage which is appearing over here. Okay, and in the second one you have stopped giving any voltage and robot is now getting driven by the link weights. Okay, that is the torque that is coming from the link side of it. It is maybe because of the external force or due to the payload or due to the weight of the links itself. Okay, so that is coming here. So now there are two things, as I have said. This is the first one, when you see there is motor displacement due to the voltage that is there. This is the forward transfer function, that is motor is driving your system. In this case, for a very large value of gear ratio eta, the term containing tau ls may be neglected. That is what is neglected, as I have said. So anything that is coming from here is now neglected. Okay, so that is neglected and closed loop transfer function is given by this. This is the first case. In the second case, you don't apply any voltage, VA becomes equal to 0 and it is getting driven by the load torque itself. Okay, in that case this is your transfer function. KE and KM, you see both were appearing in product, so that is visible here, and that is this one. Okay, so the effect of load torque on the motor angle is now reduced by the gear ratio eta. Okay, so that is always there. This we have seen earlier. So normally for industrial robots, electrical time constant is very much smaller as compared to mechanical time constant. Time constants are the terms which are written here. LA by RA is electrical time constant. It is very smaller than IM by BM. Okay, IM by BM, so that is your moment of inertia by damping coefficient. So that is very high significant as compared to this. So I can ignore that, dividing whole of this by RA and ignoring the terms which are containing LA by RA, you get to this. Okay, and this from the second one. So this is from the first one, this is from the second one. Got it? Okay, when I moment of inertia is only Im, B is, which is here, is sum of moment of inertia. It is sum of Bm and Ke Km by Ra. So those terms, if you substitute, you can get to a very simple term which is like this. So I'll just highlight them. So first is this, next equation is this, where I is this and B is this. I and B are these. Okay, this becomes your very fundamental equation for any industrial robot. Okay, this is your transfer function in both the cases, when you are driving using the voltage and you are getting driven by the load and not applying any voltage to the motor. Okay, so these are the two transfer functions. Okay, so now using Laplace transform of these two transfer functions that we have obtained, this one and this one. Okay, so I can get to this in transfer function, taking initial conditions as 0. All these initial conditions are assumed to be 0, and this is your relation. Okay, so the transient response before attaining steady state depends on the time constant I by B of the closed loop. That is basically the part of the equation which is there over here. Okay, that becomes your characteristics equation for this transfer function, that is in the denominator. So I by B, basically if you take B common, so that gives you the root, and that only governs your system. Okay, that only governs your system, that is the input and output relation. Okay, so time domain expression for this may be obtained by taking inverse Laplace. You know, you can obtain the time domain solution. So this is your differential equation for that. Okay, and you have now UA minus TD. What are those? TD is the disturbance input, that is from the load side of it. I am seeing this load as a disturbance now. This can have a payload, this can have supplementary load, or it can have some sort of external forces as noise. So that is now my disturbance force. This is your control input which is there. That is what should be desired by the voltage which is here, and this is your system which is getting driven. So now effective inertia I, you know already what was that, and the B terms, so that was written here. So I and B are here, so that is what is here. Okay, and now you can write your system in very simple form like this. So here you were getting theta m dot. So if I integrate it, that is 1 by s, that as a Laplace integrator can be written as 1 by s, so it should give me angle. So this gives me my angle. This is my transfer function of the system. Inertia and damping is present here. This is your disturbance, and you have control input u, which is shown over here. So this is your u which is here. So yes, this is your system. That is very simple. Okay, it becomes a single input single output system. Okay, you have ignored the load that is coming due to the torque that is coming due to the load side of it. Okay, so now let us take one small example by taking a data sheet of Maxon motor. Okay, so let me just show you that data sheet first. So this is your data sheet that I am using now. Okay, so you see there are many motors which are there. Parameters that we have just discussed are mentioned here against different motors which are here. So I'll be talking about the motor which is 110117. Let me see where it is. So it is the first one, 110117. So it has various constants which are mentioned here. The specific one which I'll be using is moment of inertia of the shaft. Where is it? So you see time constant is here, torque constant Km is here. Okay, terminal resistance, rotor inertia, that is moment of inertia. But you see you have to mind the units which are here, convert it to appropriate SI system if you are working with that. Okay, terminal inductance and resistance. These are inductance L, Ra is the resistance. Okay, torque constant Km, speed constant. So you see this is the data sheet that I am using, that is for the motor which is manufactured by Maxon. Okay, so now let me come back to my slide. Okay, so this is it. So I have just copied all the values, converted to appropriate units. Okay, torque constant, back EMF constant, so all these parameters were there. You can just come back and see that. So this is considered based on the torque constant which is given in M. Gopal's book, that is controls book. And Ra, if it is not given, you can take some standard value. Thermal resistance, that is the resistance only. Inductance is here. Mechanical time constant Tm is here. This is the mechanical time constant, so that you know it is 20.5 millisecond which was there. So now let me use this. So it is Bm is nothing but Im by mechanical time constant. So time constant is I by B, you know that. So Bm, you can obtain Bm, that is the damping, equivalent damping like this, and total B will be Bm plus Ke Km by Ra. That is what you have derived just now. So that is calculated like this. So Ke and Km are here. Okay, and resistance is known. So total viscous coefficient is here. Okay, so now taking inverse Laplace of the simplified motor model that we have seen just now in time domain solution, it can be written as this. Initial conditions are assumed as 0 when you take inverse Laplace. Okay, so this is your behavior of your system. You can just plot this and you can see. So using MATLAB, you can define the systems. All the constants are defined. B effective, Bm is here. Everything that we did analytical just now, we can put it to MATLAB and get the things done. So numerator has the coefficient which are like this, okay, Km by R and A. Okay, denominator is, for the speed you have denominator that is given by the polynomial I and B. Okay, similarly denominator for the shaft angle is I, B and 0 was there. So these are there. So you have roots of the denominator which is here, that is for the shaft angle I am storing here. Real and imaginary parts are segregated here, and I have done the plots for real and imaginary, that is the poles plotting I have done. Okay, again for the omega part, that is d theta by dt part, that is theta dot part, you have numerator, you have denominator which is given by, for the speed it is given by this. You have created your system using the transfer function with numerator and denominator like this, and plotted the step input of that. So this time it is step input for your system for speed and system for angle against time. Okay, time is varying from 0 to 0.3 seconds only. This is your step, and let us see how does it look like. So you have poles given by, one of them will be here, other is here. Both are on the real number line towards negative side of the complex plane, and you see you have for system angular speed, it goes something like this. Okay, and in case of angular position, as soon as you apply the voltage, it gradually picks up and keeps on changing, almost like linear. Okay, so it goes like this. Okay, and in case of angular speed, it picks up and goes there. So this is how you can analyze any motor using your standard analytical techniques like transfer function method I have used. Okay, I have drawn the poles and saw everything is okay, it is not unstable and all, so it is done. Okay, using MATLAB Simulink also you can define your system motor speed and the motor angle transfer function, put the step inputs and plot them here, and you can study it this way also. Without getting into programming, you can do this. So but this one is very well convertible to the Python code also. Okay, so that can be done. And yes, so that's all for today. So you see we have now studied the way how transfer functions, Laplace transforms, those tools can be used to study the robot joint, you know. So your robot joint, you see how does it behave. It is basically, I have considered the DC motor model for here, but you know the fundamental principle tau is equal to Km into I is same, because the conductors are lying in the same manner even in synchronous motor. So the motor equation should not vary much. There are other parameters also which can go little different, but yes, the analysis should be somewhere around this. So okay, so that's all for today. Thanks a lot.